Today, we are tackling one of the most powerful and fundamental techniques in computer science and optimization, dynamic programming. It has a notoriously intimidating name, but the core idea is beautifully simple and elegant. We'll explore the theory developed by the brilliant Richard Bellman, understand his principle of optimality, and bring it all to life with a classical Python example. So let's get started. First things first, let's talk about the name. Richard Bellman, the mathematician who developed this method, admitted he chose the name dynamic programming mostly because it sounded impressive and would help him get his research funding. Programming didn't mean coding, it meant planning, and dynamic just made it sound more sophisticated. The actual concept is more intuitive. Dynamic programming is a method for solving complex problems by following a simple mantra, which is break it down and solve each piece once and remember the answer. That's it. You break down a big problem into smaller overlapping subproblems, solve each subproblem just once, and store its solutions so you never have to solve it again. So let's use a tourist dilemma analogy. Imagine you're trying to find the shortest walking path to a landmark in a new city. You could try exploring every single path from your hotel, which would take forever. Or whenever you reach a new intersection, you could figure out the shortest path from that intersection to the landmark and then write the answer down on your map. The next time your journey takes you to the same intersection, you just look at the map instead of re exploring. You're remembering past results to make future decisions faster. That is the essence of dynamic programming. The entire theory rests on the central insight from Bellman, known as the principle of optimality. The formal definition is a bit mouthful, but what it means is incredibly simple. Any optimal path is made up of other optimal paths. Let's go back to a tourist. If the shortest path from your hotel to the Eiffel Tower possesses through the museum, then the part of your path from the museum to the Eiffel Tower must be the shortest part between those 2 points. If it wasn't, you could just swap in with the shorter part to improve your total trip, which means your original part wasn't the optimal to begin with. The Bellman equation is just the principle of optimality expressed in mathematical form. It's the engine that drives dynamic programming and modern reinforcement learning. This formula formalizes the chess master's logic. Think about how a grandmaster evaluates the position on the board. They look at the value of their current state. To figure that out, they consider every possible move they can make. For each move, they add the immediate reward it gives them to the discounted value of the future board position they land in. Then they simply choose the move that maximizes the total. That's exactly what the Bellman equation describes. There is no better way to understand dynamic programming than with the hello world of dynamic programming, the Fibonacci series, where each number is the sum of the two preceding ones. The most obvious way to code it is with a simple recursive function, which you can see here. This code is elegant and correct, but it is disastrously slow for even moderately large numbers. Like for example, let's see for 35 here. So, using the naive approach for 35, we got the answer in somewhere around zero point 0.5 seconds, right? So, now if we plug in 40, let's see how much time it will take. So, it took us approximately 6.1 seconds to compute the value when n is equals to 40. This shows how slow it is even for small large numbers. So, why is it this slow? Because it keeps recalculating the same number of values over and over again. For example, if you look at the recursion tree for calculating the fifth Fibonacci number, we calculate the Fibonacci number of 3 twice and 2 3 times, and so on. This is what we call overlapping subproblems, and it's exactly what dynamic programming is designed to fix. Our first DP approach is memoization, or a top down method. This is a write it on the map strategy. The code looks almost identical with the previous recursive code, but with one crucial difference. We have added a memo dictionary. Before we compute anything, we check if the answer is already in a memo. If it is, we return it instantly. If not, we compute it, store it in the memo, and then return it. Let's run this for n is equals to 100. So if you can see, it took us zero point 0.0 seconds for n is equals to 100, whereas the recursive code took us 6.1 seconds for just n is equals to 40. So this is how fast calculating a Fibonacci number becomes when we can just keep a track of what calculations or subproblems we have computed earlier. Now, let's look at the second approach. This approach is tabulation, or the bottom up approach. Instead of starting from the top and going down, we build our solution from the ground up. We create a table or an array, and we know the answers for 0 and 1. Then we just loop forward, filling in the table for 2, 3, 4, and so on until we reach our target. This is often even more efficient as it avoids deep recursion. So now let's run this code. Again, as you can see, it's as instantaneous as the snippet of memoization. So, Richard Bellman's theory of dynamic programming is a profoundly powerful idea hiding behind a slightly confusing name. The principle of optimality gives us the logical foundation to break problems down. The Bellman equation gives us the mathematical recipe, and the techniques of memoization and tabulation are the practical tools we use to achieve these massive speedups. By solving subproblems just once and remembering the results, we can solve a huge class of optimization problems that would otherwise be impossible. This idea is everywhere, from Google Maps routing you home, to AI learning to play games, to complex financial modeling.